Welcome. Here's the standard 3x3 magic square. It's the numbers 1 through 9 in a 3x3 grid with a property that each row, each column, and each diagonal adds up to 15. This is a very famous example. It's been around for centuries, and people enjoy its magic properties, namely these row and column and diagonal sums are always the same. But this magic square actually has another magic property not as well known. So let's imagine two people playing a game. Albert is going to choose any number at random from the first row, and Bilbert's going to choose a number at random from the second row. And whoever chooses the highest number wins. That's this game. So there are lots of possibilities. Maybe Albert will choose a 6, maybe Bilbert will choose a 5, in which case Albert wins. If, say, Albert chooses a 1 and Albert chooses a 7, Bilbert wins. So let's analyse who's going to win this game. What's the chances of A beating B? What I'm going to do is draw a table on the side of all the possibilities for Albert. He can choose 6, 1, or 8. This is Albert's choices. Bilbert can choose 7, 5, or 3. And let's just analyse who wins in each possibility. For example, if Albert chooses 6, Bilbert 7, Bilbert wins. 6 beats 5, Albert wins. 6 beats 3, Albert wins. And if Albert ever chooses a 1, we can see that Bilbert's going to win in every single case. And if Albert chooses an 8, we can actually see that Albert wins in every single case. So of the 9 possibilities, we see that Albert wins 5 out of 9 times. The probability of Albert beating Bilbert is 5/9. Well, Bilbert and Cuthbert would also like to play this game amongst themselves. Cuthbert's going to choose a number at random on the bottom row. Let's analyse their game. Here's Bilbert. He can choose 7, 5, or 3. Cuthbert can choose 2, 9, or 4. Let's analyse who wins in each of those cases. Going by columns, if Bilbert ever chooses 7, he wins here. Cuthbert wins with a 9. Bilbert wins with Cuthbert choosing a 4. Here we see that Bilbert wins, Cuthbert wins, Bilbert wins, and if Bilbert chooses a 3, Bilbert wins here, but loses on the 2 other cases. But overall, we see that Bilbert is winning 5 out of 9 times. The probability of Bilbert beating C is actually 5/9. Well, what about Cuthbert and Albert? Let's analyse their game. We'll see if I can squeak it on the side. Here's Cuthbert. He can choose 2, 9, or 4. Here's Albert. He can choose 6, 1, or 8. And of the various options, we see that Cuthbert wins here, and Cuthbert wins here, 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 and Cuthbert wins. Look, that C is very handy there. Otherwise, Albert's winning in all other spots. But look, out of the 9 possibilities, Cuthbert's winning 5 times. The probability that Cuthbert beats Albert is also 5/9. So we have this very strange property. This magic square has the sense that in some sense row A always beats row B 5/9 of the time. I should have said always then. Row B beats row C 5/9 of the times, and row C is stronger than row A. It beats it 5/9 of the time. Welcome to this non-transitive property of this magic square. A beats B, B beats C, C beats A, each with probability 5/9. Very weird. Normally if A is bigger than B and B is bigger than C, we conclude that C therefore must be smaller than A, but actually we don't. We have C is bigger than 8. Well, this actually probably works with columns too. Choose D, E, and F. If you work out the probability the same way, the probability that D beats E is actually, again, 5/9. And E beats F 5/9 of the time, and F beats D 5/9 of the time. This magic square has a wonderful non-transitive property. Well, is it true just for this magic square or other magic squares as well? Well, this magic square uses the digits 1 through 9 in the 3x3 grid of 9 cells. Here is the 4x4 magic square using the digits 1 through 16. Take me a little moment here just to redraw it. So, whoops. And the numbers go something like, you can order it in any rotation or reflection you like, but here's one standard way of doing it. 2, 13, 8, 11, 16, 3, 10, 5, 9, 6, 15, 4. And you might want to pause this video for a moment and see if Albert, Bilbert, Cuthbert, and Dilbert play this game. You'll work out the probability of Albert beating Bilbert, and the probability of Bilbert beating Cuthbert, and the probability of Cuthbert beating Dilbert, and the probability of Dilbert beating Albert. You'll find these are, again, all equal. But however, it's not quite as impressive. You'll find each of them wins 8 out of 16 times. But check column-wise as well. What's going on there? Whoops. Dilbert, Egbert, Filbert, and Gilbert. So here's my challenge. Is this probably true of all magic squares? If I give you an n by n grid and we fill it with the numbers 1, 2, all the way up to n squared, do these magic squares always have the additional property of this non-transitivity, that the probability of column A beating column B equals probability of column B beating column C, and so on in a cyclic fashion, ditto for the rows? That's a good mysterious question. So what you might want to do is go hunt for other examples of magic squares, work out the probabilities, and see what's going on. If something's going on, there's a mighty good challenge to prove. If something is not going on, this is just all a wonderful coincidence. So which is it, I wonder? Thanks.